Today we are going to discuss about hyperspectral remote sensing for soil characterization and estimation. As you know, till now you might have been taught the potential of hyperspectral remote sensing, its principles and various applications, and these last two classes will be on the soil and vegetations. As per the definition told to you by many speakers, there are three criteria which meet the requirement of hyperspectral remote sensing. The first one is narrow bandwidth. It should be less or equal to 10 nanometer, large number of bands, and continuous. So you have maybe the number of bands 60 and it should be continuous, and bandwidth may be less than or equal to 10 nanometer. And potential of hyperspectral remote sensing with respect to soil is, as you see down in the right hand side of the picture itself, the spectral reflectance curve of a vegetation and a soil and water is given over here, and which is compared with also the spectra with the bands 1, 2, 3, 4, 5, 7 of the TM sensor. If you see, if you take only those 6 bands and you draw a plot, that won't look like what you are seeing when you take a data recording at every 1 nanometer starting from 400 to 2500. And you could get a curve having a vegetation having a lot of up and down, and also in a water and a soil having a continuous curve. So that's the reason why we are looking for hyperspectral remote sensing, to look at these curves and their particular interaction and characterizing them and estimating different parameters. The most important issues in case of soil applications studies with respect to hyperspectral remote sensing or remote sensing is, never soil is open in the field. Like in case of vegetation, the sensor looks at the vegetation, maybe at a stage the crop field, maybe wheat or rice or whatever the crop is standing, maybe looking at a forest, maybe looking at a water. So the target is open and pure target you are looking at. But when you look at a soil, never soil is open. Soil is covered by crop. When the crop is harvested, soil is having residues. When residue is taken off, soil is plowed, then it is irrigated. So never soil looks like what it's supposed to be. That's the reason you don't get a pure spectra of a soil. That is one limitation. Second limitation is, as you see the spectra of a vegetation, there are a lot of up and down, troughs and peaks in case of vegetation, because of their unique interaction at the red bands, near infrared, and also SUI ranges. So based on that, you are able to characterize the vegetation much better way, and based on that you are able to have so many indices in case of vegetation. But looking at the soil, you don't get so many up and downs. That means soil's interaction, electromagnetic spectrum interaction in different wavelengths is not that strong as compared to the vegetation. And that's the reason we are not able to, that has been a challenge for remote sensing people, also soil scientists, to characterize soil with respect to remote sensing much better way what you are able to do through vegetation. So with these two limitations, here the approach is how hyperspectral remote sensing can help us to characterize or estimating some soil parameters. Coming back to the spectral reflectance of the soil, if you see the spectral reflectance of the soil, there are a number of factors which affects the reflectance. And those major parameters are surface conditions, particle size, that is the texture, organic matter, soil color, moisture content, iron oxide content, mineralogy, and there are some other parameters also, but these are all major. Coming back to the surface conditions, the surface conditions means the surface, how the surface is covered. It may be covered by residues, it may be covered by, it may have the crust, or it may be irrigated as I told you. So the surface, if the surface is smooth, then reflectance is high. So this is how the surface condition affects your reflectance. Coming back to the particle size, higher the particle size, the reflectance is going to be lower throughout the wavelength range starting from 400 to 2500 nanometer. If you look at a clay soil, if you look at a sandy soil, the sandy soil will reflect high compared to the clay soil, but in the lab condition, the clay soil reflectance will be higher and sandy soil reflectance will be lower. In the field condition, what I said is true. The reason is, in case of field conditions, the heavy clay soil, they have a high water holding capacity, so they may keep on holding the water with them and it may have more organic carbon content. So that indirectly contributes to the reflectance, and that's the reason why reflectance goes down throughout the wavelength range if you look at a heavy clay soil compared to loamy soil, which is given here. If you look at two soil types having similar organic carbon content and pH. Coming back to the organic carbon content, more the organic carbon content, less will be the reflectance throughout the ranges. Coming back to the pH, you have the same soil texture and organic carbon content, but the higher pH have the less reflectance throughout the ranges. Then coming back to the soil color, which dominantly affects the visual range of the electromagnetic spectrum. If you have soil color due to iron oxide or aluminum oxide, which indirectly contributes to the reflectance pattern. Then coming back to the moisture contents, which affects also reflectance throughout the wavelength range, means higher the moisture content, what will happen is the reflectance throughout the wavelength range starting from 400 to 2500 will be less. Of course, there are some water absorption bands. We will come back later how using hyperspectral remote sensing or those water absorption bands we can estimate moisture content. Then coming back to the soil mineralogy or clay minerals, you see over here there are three clay minerals given over here. A is the reference panel, which is taken as a barium sulfate plate. The spectral reflectance starting from sometimes around maybe 0.9 up to 2.5 I am showing over here, which has major water absorption bands. And you see the B, C, D. B is the kaolinite mineral, C is the natronite, and D is the light. When you look at the kaolinite or muscovite kind of mineral, the spectra is more governed by the structural hydroxyl water content, and which affects the reflectance at 1.4 and 2.2, which is very strong, and it has a weak effect at 1.9. So based on that, one can differentiate kaolinite, muscovite from other minerals. Then coming back to natronite, there is a distinct 1.4, 1.9 micrometer reflector absorption because of adsorbed water, and that absorption is very weak at 2.2. Then coming back to kaolinite, again a slight response at 1.9 because of small amount of iron oxide. Then in case of light, constantly low reflectance, less than 1.7 micrometer, and minimum intensities at 1.4 and 1.9 because of low adsorbed water content. So based on these typical absorption features, one can differentiate different mineral salt clay mineral types. Let's look at how hyperspectral remote sensing both in lab and field conditions, and also ground-based and the spaceborne sensors, we can do soil characterization. If you look back the literatures since 1970s, people have been working on characterizing the soils and their attributes. You see the listing of the soil attribute, so many parameters are listed over here, and these are the references given over here starting from 1971 till 2012. We can get through some publications. They tell different sensitive spectral regions which affects these particular soil attributes. You may look for carbonates, you may look for iron, maybe nitrogen, pH, carbon, organic matter, texture. So people have reported at different time what are the sensitive spectral regions which can be used to characterize all these soil attributes. So here today we are going to discuss how hyperspectral remote sensing in the ground and also spaceborne we can characterize. So we have done some study in Jalandhar regions, this is the Jalandhar district where we have a patch where the Hyperion sensor pass was there, 7 by 100 kilometer, and so the purpose was to evaluate the hyperspectral remote sensing potential with respect to soil characterization, both in the lab, field, and satellite based. So that's the reason why the 7 by 100 kilometer was chosen, though the variability with respect to soil activity is not going to be much. And this red dot points you are looking at here is the in situ spectral observations, and also soil sampling was done to do different soil parameter estimation in the lab conditions. Almost 85 locations were identified, soil sample was collected, in situ spectral observation was collected, core sample was taken for different physical parameter estimations. Of course, they are geocoded with GPS data points we have. Then in situ reflectance data was collected using field spec 3, which was having a spectral range starting from 350 to 2500 nanometer. In laboratory, all those chemical was analyzed. Finally, in the lab condition also, we have taken the spectra having the processed soil sample. Then also with the contact probe in the lab condition, having a calibrated source of light. Then we have taken the same soil samples to the field outside of the building. Under the sunlight, we have taken the spectra. Then of course we have taken in the field. Then we compared with the Hyperion. So we have 4 stages, 4 conditions at which the hyperspectral data collected were evaluated with respect to the sensors. The sensor is the spectrometer, which is a ground-based sensor. With respect to the satellite sensor like Hyperion 11 data. Then the condition like in field condition, in the lab condition, having a one calibrated source of light, having a contact probe by which you get a pure spectra. Again going back outside, having a pure soil, which is a processed 2M sieved soil, having under the sunlight. Then of course in the field conditions, when the satellite was passing, in field condition how the spectral behavior is changing. And these are the parameters which is listed over here, which are chemically analyzed in the lab to evaluate or to develop some models, estimation of all these parameters using hyperspectral reflectance data recorded through the instrument. As I told you, since the area covered was 7 by 100 kilometer only, the variability is not much. So you see the descriptive statistics, you see the minimum, maximum, mean, and standard deviation. The variability with respect to soil attributes are not much. So this is not advised to have a study to develop a prediction equation having a very limited area and develop equation which may not be much, which may not be generic or won't be applicable to all cases. So, but as I told, the purpose here was to evaluate ground-based and space-based sensors with respect to the soil parameter estimations. So that's the reason we have chosen this, though it's a limitation for the study. Already I have discussed all these things, how the spectral data were collected, both the disturbed sample, undisturbed sample, and also using contact probe in the lab, and also direct having a calibrated source of light, and in situ in the field conditions. And this is the instrument, field spec 3 spectrometer, which is from ASD, Analytical Spectral Devices USA, having a spectral ranges starting from 350 to 2500 nanometer. So there are few issues which has to be answered before developing prediction model or quantifying the soil parameters. The first foremost thing is, what should be the optimum bandwidth at which I should record the data? So the instrument which we have used, it was recording the data at every 1 nanometer. So what we wanted to do, what we did is we wanted integrating at every 5, 10, 20, 30, 40, 50, 60, 70, 80 nanometer, and develop the prediction models and look for the R square to see which the bandwidth is optimum as far as the prediction model is concerned, as far as the reliability of that model is concerned. So if you see at 5 nanometer, out of 1 nanometer, when you have a 1 nanometer starting from 400 to 2500, we have something around 2000 plus bands. But if at all integrate those data at 5 nanometer, you have 430 bands. When you come down to 10 nanometer, it's 215. In 20, 30, 40, 50, 60, 70, 80. So from hyperspectral down to the multispectral it comes down. So the question was, what should be the bandwidth at which we should look at so that the prediction model will be quite good to estimate the parameters. So as I told, you see the parameters where nitrogen, phosphorus, potassium, like this, as I listed 17 soil parameters, and here is down here is the bandwidth at which the data were integrated, prediction model was developed, 5, 10, 20, 30, 40, 50, 60, 70, 80, and the prediction equation was developed and its R-square was evaluated. And here the R-square is plotted against the bandwidth, and as you see, almost in all the parameters, as you see in the 10 nanometer found to be higher model R-square value. So that indicates the optimum bandwidth should be 10 nanometer. One should be at 10 nanometer than at 1 or 5 or 30, 40 or 50. So that's what the conclusion we arrived at, and based on this, rest analysis we did at 10 nanometer. So this is the region in which the study was conducted. It shows hardly there is any variation with respect to the soil order. Two soil order were dominating over there. One is insecticells, another is lenticels, having total 85 soil samples covering 58 and 27 samples in these two orders. And down in the background is the soil map, which was taken from MBSS LOP and borrowed from Punjab Remote Sensing Center, Ludhiana. And when you see them out of 85 soil samples, so when you classify them into these classes, we got 4 classes. There's typic haplostepes, typic ustipfluvents, typic ustisamens, and typic ustucrepes, and the spectral pattern look to be different. In case of haplostepes, relatively higher overall reflectance you are able to get, and also high calcium carbonate you are having. In case of ustipfluvents, which are fluvial soils, you have higher silty content and clay content. That's the reason why you get low reflectance throughout the ranges. In case of ustipsaments, very high in sand content. That's the reason you may have also reflectance throughout high. Then ustucrepes also, you are getting high reflectance in visible and near infrared regions. The purpose of saying over here is, though 2 soil order types you had, but when you see to these 4 types of soils, all 4 typical reflectance pattern is going to be different. We have done also another study having 87 soil samples, 23 soil series, and 4 soil orders taken from 4 locations of the country, one from Nagpur, one from Pantnagar, one from Delhi itself, another from Ranchi. So, and they are mollicels, verticels, insecticels, and alficels. And if you see the spectral pattern starting from 350 to 2500 in the lab conditions, you see how the very differentiable spectra you are able to get. When I highlight, coming back to the visible range, you can see here from 350 to 750 when I plot them, you see in case of alficels, you have kind of a concave kind of a curve in case of alficels. Insecticels almost a flattened one, and verticels you have a convex kind of spectral reflectance pattern in the visible range. So these are because of attributes of the soil parameters, or the soil attributes, because of which the pattern of reflectance is changing, and the attributes may be organic carbon content, maybe iron oxide. So I think much detail is covered in a mineralogy lecture, so I don't need to cover much detail into that. When you coming back to the near infrared range, that is from around 700 beyond to 1000 or 1110 nanometer, you are also able to see the cluster of spectra differentiating all these 4 soil orders, that is alficels, insecticels, verticels, and mollicels. And most interestingly, when you go to SUI ranges, that is from 1100 to 2500, we are able to get strong water absorption bands at 1400, at 1900 and 2200. So which is because of, as I told, maybe because of hydroxyl atom, maybe adsorbed water, maybe so because of which you will be able to differentiate which is mollicels, verticels, insecticels, and alficels, which in detail I have discussed in the previous slide, and also in case of mineralogy class you might have known. When you look at the mineral, the absorption bands are particularly because of some unique interaction of that molecule with the electromagnetic spectrum, based on which, and that is a typical unique characteristic of that mineral, based on which one can characterize the difference of that mineral from other classes. Look at the clays, the verticels, where you have a different percentage of kaolinite, smectite percentage, the reflectance pattern is changing. So having same verticals also, you are having reflectance pattern different because of kaolinite or smectite percentage or the clay percentage. So what I mean to say is, even if within the vertical types, even within soil series, if the change in texture content, change in mineral type, you will be able to differentiate the spectra. And if you see, these three names are nothing but the soil series name. They are named by local names, Beni, Fulbag and Patrakata. Here, this reflectance curve shows the three soils having different kind of organic carbon content. As I told you before, higher the organic carbon content, throughout you will have reflectance pattern less when compared to the less organic carbon content. And also same with respect to the texture. If you see the clay loam texture, you have in the red pattern of the spectra. In case of blue, you have silty loam, which is a bit coarse texture, then sandy, which is a coarse texture soil, so high reflectance. So different soil, the reflectance pattern is going to be different. Different absorption bands you are going to get, based on which one can characterize what kind of soil it is. Now coming back to the estimation of soil parameters, the first and foremost thing what we have done here is we have taken the 400 to 2500 the spectra and relate with the attribute which we are looking for. For example, I am looking for organic carbon content, so I had 87 soil samples from which 2/3 samples was taken for development of the prediction model and rest 1/3 for the validation. And if you see here, the spectral reflectance from 400 to 2500 was related with the organic carbon content value. So we got the correlation value from 400 to 2400, which is plotted over here. And you can see the correlation value when you see from 400 to 2400, it from minus 0.1 to increases to minus 0.5, then it remains stabilized throughout maybe minus 0.5. The organic carbon content and reflectance, they are negatively correlated to each other. As I told you, higher the organic matter content, more will be the less will be the reflectance. That's why negative value you got. And you see here, the organic carbon content is given here 0.2, 0.5, 0.6, 0.8 and 1.2. And based on that, the reflectance pattern tells you the lower the organic carbon content, higher the reflectance, and the vice versa. What I mean to say over here is, simply based on the correlation analysis, one can guess this is the region which is very sensitive with respect to organic carbon content, because highly correlation value you are able to get here. Same thing is zoomed over here. So based on this, all soil 17 parameters were analyzed based on simply correlation analysis. You can look for calcium carbonate. Same approach was followed here. So all 17 parameters, you can see the sensitive regions of different attribute is identified. As I told at the beginning, through some slides, through the literature, people have identified different sensitive bands for different soil attribute. Same also we could find over here. Not only that, we could find also some second sensitive spectral regions, if at all you don't have the sensors at this range, or this is the second ranking sensitive regions which can be used for characterizing these parameters. When you look back to the literature, there are some attributes which are reported with respect to spectral regions, some are not. We could report over here for whole 70 spectral parameters. So based on which we try to look at those sensitive bands and develop the prediction models. Coming back to the second issue is whether we should consider only the raw data, the reflectance data which you are getting from through the sensor, or we should go for some kind of mathematical transformation. So you can see here, this is the reflectance data on the top curve over here, which can be converted to observance taking 1 by log 10R, and again mathematical manipulation can be done if you can take the first derivative and second derivative. As you understand, if you take the first derivative of velocity with respect to time, that's the first derivative of the del v by del t, you will be able to retrieve some more information that is whether the velocity is uniform, accelerated or retarded. That means if you take a slope, if you take a derivative, you are going to get something better information than what you are having here. As you look at here, the reflectance or absorbance value, the curve looks to be very simple. It doesn't have a lot of up and down. When you look at first derivative, there are many peaks you are able to get. That means we are going to get some information at those peaks, and there is something is happening. What is that is how the reflectance pattern is changing with a little change in the wavelength. That is how the slope is steeper. That is what quantified in case of first derivative. Same also in case of second derivative, how quickly it is changing. So using this first derivative and second derivative of reflectance, first derivative and second derivative of observance, we would like to evaluate whether out of these 6 spectral parameters, which parameter looks to be good with respect to prediction of the soil parameters. As you see here, again, all those parameters, we develop the prediction equations with respect to reflectance, with respect to first derivative, second derivative, observance, first derivative and second derivative of observance. You see the predicted equations R square value. When you take the reflectance or observance, the R square value is somewhere lies around 0.3. When you go to the first derivative or second derivative, the R square value almost got doubled. That means first derivative or second derivative, what are the mathematical transformation we have done, it gives more information than the raw spectra what you have taken. So the suggestion, recommendation is one should look for the spectral transformation and use those for retrieving the parameter like soil parameters for better understanding. Same also in case of vegetation. Tomorrow we will be discussing in detail. When you take the first derivative spectra, starting in the red edge, so red edge we are able to quantify much better stress conditions than any other means. Then the third question to be answered is how many number of variables I should have in my prediction equations, whether I should take 5, 10, 16, how to optimize my number of variables. So here again, what we did is we took, as per the ranking, correlation ranking, we took 10 fast sensitive bands, then 12, then 14, 16, 15, like that 30 bands we have chosen for developing prediction models for all these parameters. And as you see here, when you see the adjusted R square, it keeps on increasing up to 15, then it goes down. That means after 15 variable, if you keep on adding some more bands, the reflectance or observance value in different bands, hardly you will get any more information or any improvement in the R square value. That indicates this is the optimum number of bands which can be used to develop the prediction model. So you see here in the table, the whole exercise result is given over here. For different parameters, the number of bands chosen was given over here. Like for example, for nitrogen, 18 bands was chosen, that is the best to be found. For phosphorus it is 12, for potassium it is 19, for iron it is 20, and adjusted R square values, which looks to be quite good as long as reflectance data in the lab condition is concerned. Then, having identified these 18 variables using simply stepwise regression analysis, we could develop prediction model. So this is the prediction model for nitrogen, this is for phosphorus, then for potassium, calcium carbonate, organic carbon. Like this, we have developed the prediction model for almost all these parameters. And you could see how many number of bands we have and also adjusted R square. So the expression says this is a constant value over here, and here A prime means this is the first derivative of observance value, and the subscript given over here is nothing but that first derivative of observance value at that wavelength. So like this, one can understand what is that. For example, this R double prime means this is the second derivative of reflectance at 1985, the spectral value. So like this, all the prediction equations were developed, and then it was evaluated. How good is my prediction equation? Of course, the R square value is given here, but we went for simply statistical parameter or statistical method to evaluate that, and we had 1/3 sample to validate my prediction equations. So there are two statistical parameters which is considered while developing the model and also developing the prediction equations. One is called standard error of calibration, that is SEC, which is given here on the mathematical expressions. The other one is standard error of performance, how good it is performing. The equation is given over here, where ym stands for whatever the measured value you have, and yp stands for how the predicted value is. NC is the number of sample for calibration, NP for number of sample used for validation, and N is a number of independent variable used in the model. Like in this case, we have 18 variables we have used. Then there are two other parameters, statistical parameters, which is considered to evaluate how good is the model. That is called RPD, that is range prediction deviation, which is nothing but standard deviation divided by standard error of predictions. Then there is RER, that is range of validation of data set or standard error, which is nothing but the range divided by standard error of predictions. So when you went for validation, we could see here the nitrogen measured and nitrogen predicted. This is 1:1 line, and down there the variable number is given, that is how many number of variables we had, the bands, adjusted R square value is given, mean value is given, and standard error of prediction is given. So this is for nitrogen and phosphorus. Same also for other parameters like potassium, iron, copper, zinc, and organic carbon content. The question lies, is that all the parameters is to be the prediction equation developed for all the parameters is reliable? Is that prediction, whatever the predicted value is reliable? So that evaluation is done while plotting with respect to RPD and R square value. As I told, RPD I told and RER value I told. So you can see here, the data points which are lying towards a higher R square value and higher RPD value. Same also in case of RE and R square. Those are highly predictable in nature, in the sense the reliable result you can get using this prediction model, these parameters. Look at down on the curve on the left hand side where you have RPD value low and R square value low. That is, those parameters, for example, pH, PD, bulk density, zinc, they are found to be not predictable. That means it's not true that all the parameters can be predicted. There are some parameters which prediction model doesn't hold good. So this is what in the lab condition the prediction equation was developed. So same, let's have a feeling of going to the field what happens, and also in the satellite level what is happening. So as I told, we have synchronized the satellite pass and we have taken the spectral data in the field conditions also. And the satellite data used was U1 Hyperion data, the Earth observation 1 Hyperion data, which was having 242 bands, overlapping having 20 bands. But when you see, looking at the good bands, hardly you have 158 bands. So using those 158 bands only, the rest exercise was done. And you can see the FCC of the Hyperion data of the study area, which is around 7 km by 100 km down here. This is the Jalandhar city down here. And what we did here also, whatever 158 bands we have taken, whatever the spectral ranges was chosen as a window, same also was done, same exercise was done with respect to reference data which is collected with the spectrometer. In case of spectrometer, you have data at 400 to 2500 continuous. So in this case, in case of Hyperion, we have removed some of the bands which were noise, which were overlapping, which were strips. So those wavelength ranges were taken out in case of the spectral reference data taken in the lab and also field conditions, so that we can compare the data collected from spectrometer in these 158 bands with the satellite data. So this is what in field condition the in situ spectral observation was done, and as you are very much now aware of how complex is the data processing with respect to Hyperion data processing is concerned. You need to go for atmospheric corrections. There are a lot of steps which have been taught by my fellow speakers before. So I am not going to talk much detail about that. You can look at here in the above picture down here. This says you have a field spec spectra and you have a Hyperion spectra which is not at all comparable. This is an uncorrected data. But after corrections, after running the flash, which the speakers might have told in detail, when you go for corrections, after correction, when you look at the spectra of the same pixel in the field spec data like spectrometer, and also in case of field spec, in case of Hyperion, they are almost same pattern, only the variations with respect to the spectral value, but pattern is almost same. So what I mean to say is, unless you correct the satellite data, unless you also integrate the 10 nanometer data having only 158 bands, again taking the sensor response function of 158 bands of Hyperion, one cannot compare with the satellite data. And very interesting plot over you can see over here. So that's what at the beginning I was saying at what conditions we have taken the data. So this is the spectrometer taken at contact probe. The blue curve which you are seeing over here with the contact probe, this is a pure spectra without having any noises. When you take the field spectrometer, that is AST field spectrometer, having seed means the soil was processed soil having 2 mm sieve we have taken in the outside in the building. So you get the spectra, this is the red one, you get the spectra where you get some noises at around 1400 and 1900, that is because of atmospheric vapor. And in the field condition, as you see picture before in the previous slide, when you take in the field condition, this is what the spectra you got, the black one, and this is what the Hyperion image spectra. So their pattern is almost same. So now, and you see this blue strips, what you see is those bands are not considered in case of Hyperion data, as I told, and same part is removed also in case of contact probe data and also in case of field data when you take with the field spec. Then only we could compare, we developed the prediction equations and went for comparison, how good is both lab conditions, field conditions, and also when you go back to the satellite level. As you see in this case, in case of lab conditions, the parameters considered were nitrogen, phosphorus, potassium, organic carbon, calcium carbonate, and also textures. And you see that just the R-square value, when you take the lab spectral data having those 158 bands and develop the prediction equations, R-square value is something around 0.6 away about that. Because lab spectra is very pure, you don't have any atmospheric noise, and you have process data, control conditions, calibrated source of light, so everything is controlled. So data is very pure. So prediction equation holds good when you take the lab data. But when you go down to the field conditions, what happens is, as I told you at the beginning, field is never open, soil is never open, soil has something over there, and again you have a you have a field of view of your sensor. It's looking at not only the pure spectra, it's looking at many things on the soil under that field of view. And also you have a atmospheric noises, you have atmospheres outside, you have a light condition which is not under your control. So taking to those into, you can see the R-square value has gone down, which is very much obvious. When you go back to the satellite data, which is 30 meter by 30 meter resolution pixel data, and it is around 800 to 1000 km away from you, so R-square value has gone down compared to your lab or field data. So this is what the comparative study which was done. Of course, the conclusion is one can use also the Hyperion data to have predictions for some of the parameters, maybe organic carbon, texture, which I am going to discuss now. You see here, what we have done is we have, whatever the field spectral data we have taken at 87 points, we have gone for simply geostatistical techniques and interpolated those and created an image, put this all spectra together one over other, created a kind of a image like you have in case of Hyperion. So we had around from 400 to 2500 at every 10 nanometer we have the spectra which got simulated. We got a image at every 10 nanometer and got stacked together. So that's the simulated image like your Hyperion. From that we predicted the soil organic carbon content. So this is the soil organic carbon content from the simulated image, and the simulated image is taken from the hyperspectral data collected through field spectrometer at 87 soil sample points. Then the second image you see at here is soil organic carbon content from Hyperion image, which using the prediction equations we could get it. And the third one is you have 87 point soil organic carbon content simply using interpolation techniques like IDW. You have a surface generated. So all these three were compared, and you can see here the measured soil organic carbon content and predicted soil organic carbon content, which found to be fitting oil with 1:1 line, having R-square value 0.87. Then we did some kind of study also, soil moisture estimations in IRE farm itself, which is given over here. This is a whole IRE farm. Those yellow dot plots are you seeing here, and these green points are the sampling points where we have. And in case of IRE, we had around 6 soil series which covers whole IRE farm, and these 6 soil series again in 3 depths, having around 80 samples, so around 240 samples we had. Here what I wanted to show is, we wanted to see the surface spectra, then below surface 15 to 30 centimeter and 30 to 45 centimeter. You can see the spectral value, how that's changing. That means all these soil series, the pure spectra which was taken in the lab condition collecting the sample from the field, you could see the variations with respect to different soil series. Like in case of Nagar series, which is more of a light texture soil, you have a high reflectance, where in case of Jaga series you have a bit clay and also organic carbon content high. So that's why you have low reflectance throughout. But you see the range minimum to maximum. In case of surface, you have a high, while you go down from the subsurface to surfaces 2, 30 to 45 centimeter, they narrow down. Hardly there is any difference with respect to soil series spectra. That means because surface soil is more exposed, more variations you can see. When you go down, that variation part is not there. That's why the spectral pattern looks to be same in all the cases. Not only pattern, also the value, having very narrow band in which all those spectra are falling in. Then looking at the estimation of soil moisture at different levels, so when soil was collected, you see different level of soil moisture in the field, starting from 0, that means something like 2% or 3%, you have 9%, you have 12% and 19%. That 0 is your orange one, 9% is the black one, the pink one is 12% and blue one is your 19%. And same also shown here, this is a Palam series, this is the idea of the soil sample which was collected, this is the moisture content. What it indicates is, when you have a dry soil, the spectra was like this. When you have little moisture content has gone now, so the spectra has gone down drastically. But that exponential change in the spectra doesn't happen when you go on adding the moisture content or go on looking at the soil having higher moisture content. The reason was the little change in moisture content. What happens? It goes on filling micro and macro pores in case of soil. So immediately the soil spectral pattern changes. But after that, once it gets saturated, the more addition of water, hardly there is any effect in the reflectance pattern. So that's what it is indicated over here. And when you going for developing the prediction equation, and you can see one more thing over here is at 1400 and 1900 water absorption bands. So those are mainly responsible for water content, moisture content in the soil, and mostly the near infrared range is more governed by water content than these ranges. Of course, there is a variations, but these are very sensitive with respect to water content if you go for correlation analysis study, as I mentioned before. So when we went for correlation ranking and developed the prediction equation, we could see that Y is moisture content equal to this is the equation which is given having this number of variables, and those bands 1435, 1975, 2235, 1923, all these bands are almost in near and sweet ranges, and this R prime is nothing but the first derivative of the reflectance. And you could see the adjusted R square is 0.94 and this is 1:1 line fit. That means the prediction soil moisture estimation in the near infrared range having using these band sensitivity bands looks to be a bit reliable. Then coming back to a technique called total information content index for soil moisture estimation using multispectral and hyperspectral data. So before going to that index, I would like to tell what happens in case of basic remote sensing principle is you have individual wideband which is related to only few properties of the target under consideration, not the complete set of target characteristics. For example, red band, it is mainly for chlorophyll content, or the visual range is mainly for pigment governed by. NIR ranges is mainly governed by cell arrangements, parenchymal cell arrangements. So a lot of internal reflection takes place, because of which the reflectance is high. Means you have spectral ranges which defines what the property it attributes to. But if you want to go for complete analysis of a target, complete analyzing the target, one has to consider whole spectra. So that's why use of more number of bands leads to a complicated class separability and clustering analysis. One problem was, you have a single band, you are having little information. If you have more number of bands, more complicated class separability or clustering analysis. So, but you need to have more number of bands so that your information content is getting more. So here, with that, we could develop a numerical technique by which one can compress all this data collected in different bands, which will be easy for clustering analysis and class separability, irrespective of number of bands used. And that index is called the total information content index, which is based on Shannon's information theory, which is mainly used in information technology. That is mainly used for biodiversity calculations also, how diversified is your species, any kind of diversification you are looking at. That is Shannon's diversification index. Also people look at this for the data compression technique in case of remote sensing data also. In case of information technology, people use it to compress the data and transmit it. But here we have used this to integrate all those bands to a one-dimensional index from n number of bands, so that we can characterize much better way. And the expression is given over here, that is h equal to minus n pi log 2 pi summation over I 1 to n. What is pi? Is the probability of occurrence of particular reflectance at a particular reflectance over the whole spectral ranges, and xi is the number of outcome of that event, and n is the total number of outcomes. And this is nothing but negative of entropy. And the same program is customized in program was developed for both spectrometer and satellite data in the Idrisi format, and using the spectrometer that's like a PC 1800, which was only 330 to 1100. Of course, we have upgraded this software up to 2500 right now. So you can derive different indices which are sensitive for soil moisture, and also vegetation like NDVI or band ratio. You can derive total uniform content index using Indian remote sensing satellite bands only, or any number of bands you want to have. You can view the file, you can edit them, you can go back to the main menu. Same was customized in Idrisi software, so that with the satellite data we can process and develop a TIS index. This is what the whole process is. Spectrometer data and satellite data. This is what same thing, how in Idrisi one can look for and go for calculations. And you can see here, these are different soil series numbered, and these are different bands, single bands. Okay, and the correlation coefficients, the relationship between this reflectance value got on these bands with the water content is given, which is very poor. And when you calculate a index called NDWI, normally difference water index, you could see the improvement with respect to the correlation coefficient and also regression coefficient, which is given in bracket. But when you see the total information content using only 4 bands, there is a improvement over the correlation coefficient over single band or NDWI. But when you use only 4 bands, this is what H4V stands for. But when I use like data like spectrometer, we have, as I told, 400 to 1100, at every 5 nanometer you have n number of bands. So that SW stands for, if the band number is more, like 100 bands or 200 bands you have, when you can integrate them using the same formula, you could see the R-square value has gone up like anything. And same thing you could see here, this is the prediction equation using the total uniform content calculated from n number of bands. You see the relationship with respect to different soil series. And you could see here, having the same soil, variations with respect to moisture content, you could see the differentiation with respect to the index calculated with the 4 bands, index calculated with the more number of bands. So that means this band, this technique, total uniform content index, looks to be very potential with respect to hyperspectral remote sensing, not only for soil moisture estimation, also some other soil attribute estimation or characterizations. Then we have also tried to see how hydraulic property can be estimated using hyperspectral remote sensing, using the spectrometer near the target, that's a proximal spectrometry. So what happens in case of soil, when you have a property called hydraulic property, that is a saturated hydraulic conductivity, that Ks, which is very difficult to measure. Difficult in the sense it is a very time consuming and intensive. You need to spend a lot of time and effort to have hydraulic conductivity estimated in the lab conditions. So for that, there are different methodologies people have developed, that is called Pareto transfer functions. If we can use easily measurable parameters, for example, organic carbon content, bog density, clay content, soil pH, elevation, then textures, then from there one can easily estimate hydraulic conductivity through some kind of mathematical transformation as shown over here, and that technically is called Pareto transfer function. So Ks, that is saturated hydraulic conductivity in logarithm scale, is given by this equation, where this pH, bog density, clay and elevation and silt can be measured very easily. So you can get hydraulic conductivity indirectly estimated now. And this alpha and n are Van Gonitchin parameter, which can be also estimated using Pareto transfer function. So if at all we are able to measure, as I discussed till now, we are able to estimate pH, bog density, texture through the hyperspectral remote sensing data, then I should be able to also retrieve hydraulic conductivity. So with that concept, we developed a term called spectro transfer function. This is the work in collaboration with IIT Kharagpur, which we have done. So what happens is, as I told you, the spectral reference pattern, from there one can estimate all those parameters like organic carbon, bog density, texture. Then from this spectral data also I should be able to develop this hydraulic conductivity and Van Gonitchin parameter using a similar kind of function, which is called spectro transfer function. Then for that purpose, what we did is we have used whole spectra starting from 400 to 2500, and also we have used the Landsat ETM plus corresponding bands, integrating to ETM band ranges using sensor response function of ETM. Then also we have looked for continuous removal factor, which I am going to talk in detail tomorrow also, where continuous removal factor means the water absorption bands at 1400, 1900 and 2200, which was quantified through CR factor, and the expression is given over here. That is also used to get the Pareto transfer function. So you can see the Pareto transfer function. This is the basic soil, what the soil scientists they develop using the clay or bog density or particle density. This is the hydraulic conductivity could be estimated. This is what satellite derived or remote sensing derived Pareto transfer function, a spectral transfer function rather we can say, where the spectral data which is collected through ASD spectrometer, integrated through ETM data, using again with continuous removal factor, this is what, and through principal component analysis, this is what the Pareto transfer function for retrieving hydraulic conductivity. Then only ETM data, only continuous removal factor and only spectrum, and for evaluating RMSE value is given over here. Same also with respect to Van Gonitchin parameter. That means if at all you have a spectral data collected for the soil, then you will be able to get also this hydraulic property estimated to some extent. Since we could retrieve soil parameter using these equations, so there was an approach whether we can monitor soil quality using this proximal hyperspectral remote sensing. So there is an approach called nonlinear weighted soil quality index. That is nothing but the SI is your the scoring, and the parameter, and N is your number of indicators, and WI is the weightage given to all these indicators. That means the soil quality is governed by so many parameters reported by many authors, but these are the major parameters which is taken for calculating the soil quality index. This is a composite index. Out of these all these parameters, different weightages can be given to them. The parameters which are given in white, those could not be estimated through those could be estimated through hyperspectral remote sensing. Those given in red fonts could not be estimated through remote sensing data. So what we did is, since all these parameter was used to calculate the soil quality index, so some are estimated through conventional approach, some through remote sensing. So putting them together, the soil quality index was developed, that is called hybridized soil quality index. So this is what the model which was developed by us. Same model was used here for different regions of the country, different agroecosystems having different kind of cropping pattern to evaluate the soil quality. And you could see here hybrid soil quality index, which could be estimated using both conventional soil data and also hyperspectral reflectance data. Putting them together, this hybrid soil quality was estimated. This is what the conventional approach, and this is the different kind of cropping system you have in different regions. This is the Hisar, this is Pantnagar, this is Ludhiana. So what I need to say over here is, this is what conventional soil quality index, and there is a hybridized soil quality index. Hardly you could see any difference between them. That means we can replace also conventional approach to have through hyperspectral remote sensing to estimate soil quality or to monitor soil quality, and to suggest what kind of cropping patterns should be there so that my soil quality will be restored. So at the end, the conclusion is, as we see, the optimum bandwidth should be 10 nanometer, as we have analyzed and could see with respect to adjusted R square. So, and that may be the possible reason why in Hyperion and many of the sensors the bandwidth is given 10 nanometer. And as we discussed, you know, the raw spectra, raw reflectance or its observance doesn't hold good with respect to prediction equations. We could see that derived spectra, that is a faster second derivative spectra, found to be better than the raw spectra while developing the equations for estimating different soil parameters. When you look at a regional scale, we could see that hyperspectral remote sensing data, Hyperion data, could estimate reasonably with good accuracy all soil parameters, which can be further used for soil site specific management or precision agriculture. You could see also, like Pareto transfer function people use to retrieve the hydraulic conductivity parameter or hydraulic properties, we could see that spectro transfer function can be also used to retrieve the soil hydraulic properties. That's what the very novel approach which we need to access more onto. Then you could see the potential of total uniform content index, which is more potential if at all more number of bands you have, that can be used with the hyperspectral data for characterization of not only soil, also other parameters. And remotely sensed soil quality index can, of course, partly can substitute the conventional approach to go for soil quality monitoring. In 3 ecosystems we could see. Based on the soil parameter which could be estimated through hyperspectral remote sensing, one can use for fertility mapping, as you could see organic carbon map regional which we developed. Same also can be done for nitrogen, phosphorus, so that fertility index mapping can be generated on a site specific nutrient management or precision agriculture can be done. Of course, as at the beginning I told, at the end also I would like to repeat again that the spectra which has been collected is limited to only few area, that is only 7 by 100 km, as I told in case of Jalandhar. Of course, we have collected something around 87 soil samples covering 27 soil series, 4 soil orders, but one has to look for more soils collected all over country having wide variability with respect to this parameter to make the prediction model or algorithm more generic, which can be applied for estimating all these parameters. Thank you very much for patience hearing.